Today we do an example of the integral test. Suppose we have sum n equals 1 to infinity of natural log of n over n. Now by this point we have considered special series, the p-series, telescoping series, geometric series, and nth term test. Now it turns out when you take the limit by L'Hopital's rule, it will go to 0, so we cannot really use that for divergence, and it doesn't look like any of the special series, so we have to use something else, and we learned about this integral test in our last lesson. But we cannot use the integral test directly. It has to satisfy three properties. What are the three properties? One, is it positive? Let's check this. Well, first we want to, let's do step 0. Consider a function f of x equals natural log of x over x. And for x greater than or equal to 1, well, natural log of x is equal to 0 when x is equal to 1. But we know natural log is an increasing function. So for x greater than 1, it's always going to be positive. So for x greater than 1, natural log is positive, and we also know that x is positive. And you're dividing two positive numbers, so natural log of x over x is positive for x greater than or equal to 1. Okay? Next thing we want to check is continuous. And we notice here, so on a fraction, so the ln of x over x is discontinuous whenever the denominator is not continuous, when the denominator is equal to 0. In this case, the denominator is equal to 0 when x is equal to 0. But we're only considering x greater than 1. Therefore, this is continuous. F of x is continuous for x greater than or equal to 1. And finally, positive, continuous, most important thing, and this is where the most effort is needed to be shown. So we need to show, is this decreasing? Usually we can show, is the next term going to be smaller than the current term for all n? But in this equation, another thing we could do is use facts from our derivative, in which we said if the f prime is less than 0, then f of x is decreasing, right? So we can use this fact, and let's take a derivative of ln of x over x. Now this is quotient, so we use the quotient rule. Low derivative of high minus high derivative of low, square the bottom. Here we go. So derivative of ln is just 1 over x, and derivative of x is just 1, so I'm going to leave that alone. And note, x times 1 over x, that's just 1. So we have 1 minus natural log of x over x squared. That's our derivative. Guess what we notice? The denominator is always going to be positive, right? Because it's a square term. So this fraction can only be less than 0. So f prime of x is only less than 0 when the numerator is less than 0. Well, the numerator is less than 0 only if we put everything on one side, if natural log of x is greater than 1. Well, when's that true? If we exponentiate both sides, we can see that this is only true for x greater than e, which is about 2.7. Hence, this is decreasing. So since we have shown this is positive, continuous, and decreasing, we can now do step 4. Now we can apply the integral test, which is exactly how it sounds. The series was going from 1 to infinity. Now we just need to integrate from 1 to infinity. Natural log of x over x dx. Note this is an improper integral, so we have to take the limit as t approaches infinity of 1 to t of natural log of x over x dx. And this is a classic u substitution problem. We have u equals natural log of x. If u is ln, what's du? Well, du is 1 over x dx, and that takes care of this portion. I'll erase that for now. And on this side, I'll do some scratch work. So this is basically the integral of u du, right? Du takes care of 1 over x dx. Integrating that, we have u squared over 2, plus c technically. So this is actually equal to the limit as t approaches infinity. And what is u? U was just natural log of x. So that is natural log of x, quantity squared over 2, going from 1 to t. And now, by the fundamental theorem of calculus, let's plug in the points. We have natural log of t, quantity squared, over 2 minus natural log of 1, quantity squared over 2. Well, what's natural log of 1? That's the 0. So we only have this term remaining. But as natural log, let's look at the visual. Since natural log of x is an increasing function, so as t approaches infinity, natural log will continue to get bigger and bigger, and this will go to infinity. And so we conclude that, therefore, since the integral diverged and we have checked these 3 conditions, positive, continuous, and decreasing, we can say that the series n equals 1 to infinity of natural log of n over n also diverges by the integral test. And that's it.